All right, so last time we left off, as part of the way through section 13.6, we had just derived the equations for the electric field perpendicular to a dipole. So the precise derivation is 1 over 4 pi epsilon naught q times s over s over 2 squared plus r squared to the power of 3 halves. And the approximation when r is much, much larger than s is 1 over 4 pi epsilon naught q over s r cubed, and in both cases you would determine the direction by that visual inspection. That's why those pictures are so important. Now, if you recall from when we started chapter 13, the whole purpose of learning how to calculate electric fields is so that we could calculate the electric force using the field. So we know that the force on any charged particle is going to be the charge of that force multiplied by the electric field, where the final direction of the force is determined both by this electric field vector and by the sign of the charge that you have inserted into that field. So let's take a look at the direction of force looking at a dipole. So we're going to put a charge Q here. So we've got some distance D much, much larger than S from the middle of the dipole to the direction of the charge. S, of course, is that separation between the two charges. So let's think about where the field is. Now, in this case, the electric field is going to be pointing towards the negative charge. This is because the negative charge is closer. So we'll have a field from the positive charge going up and a larger field from the negative charge going down. So that's going in negative y. And now let's think about the force. So the force is going to be equal to Q times the electric field of the dipole. So in this case, the charge is positive, so the force would be equal to, so QE dipole is equal to Q0. This is going down, so minus y, which would, oh my goodness. Let me rewrite that. So Q times 0 minus 1 over 4 pi epsilon naught 2qs over d cubed 0. So remember when you're looking at the force that you need to keep track of all of the signs of the components of the electric field, as well as the sign of the charge that you're inserting to calculate the force on it. Woo! Tongue twisters. All right. Now, the last note on that I want to say, we could also think about what then would be the force on this particle Q by the dipole, and it would be just simply equal and opposite because Newton still holds. Okay, so next up we have the electric dipole moment. And so the product of charge and separation, S, is called the electric dipole moment. So P is equal to QS. And sometimes you'll see this being equal to QD, where D is the distance between the two charges. I kind of see both used equally in different textbooks. The units of the electric dipole moment are Coulomb meters, or charge times distance. All right, so we want to go after what the electric dipole says about the electric field, and we're going to do a second derivation for the electric field on axis. And we're going to bring in the electric dipole moment. And the purpose of doing this second derivation is just to give you an additional proof for how this works and to bring in the electric dipole moment. Okay, so we have a dipole. And so the electric dipole moment is going to point towards the positive charge. And we are looking at the field at this location here. So we're going to have E positive, a smaller E negative, and E net is in this direction. And then let's just list out. So we have y plus s over 2, and then y minus s over 2. Oops. There we go. Okay, so this is the setup, and now we're going to derive the electric field on axis for this dipole using this particular setup. And for this, we are going to need this binomial expansion. 1 plus x to the n is approximately 1 plus n, oh my goodness, 1 plus n minus 1, x squared over 2, and dot, dot, dot. Okay. So starting with the derivation, the total y component EY of the electric field from two charges. So EY is equal to Q over 4 pi epsilon naught, 1 over y minus s over 2 quantity squared minus 1 over y plus s over 2 quantity squared. This is equal to Q over 4 pi epsilon naught y squared times 1 minus s over 2y quantity to the minus 2 minus 1 plus s over 2y to the minus 2, as y is much, much larger than s. Thus, s over 2y is much, much smaller than 1. Now we're going to, using the binomial expansion, for n minus 2, the s over 2y is the x, and we need only the first two terms. So 1 minus s over 2y to the negative 2 is approximately 1 plus s over y, and 1 plus s over 2y to the minus 2 is approximately 1 minus s over y. And so we have EY as approximately Q over 4 pi epsilon naught 1 over y squared 1 plus s over y minus 1 minus s over y is equal to QS over 2 pi epsilon naught y cubed is equal to P 2 pi epsilon naught y cubed, or E on axis is equal to 1 over 4 pi epsilon naught 2p over r cubed. And also, you could write E perpendicular in terms of the electric dipole moment as approximately 1 over 4 pi epsilon naught p over r cubed. And there you have it. All right, so let's do an example. A dipole consisting of point charges plus 9.8 nanocoulombs and minus 9.8 nanocoulombs separated by a distance of 1.2 centimeters, has its center at location minus 0.02 minus 0.230 meters, a ping pong ball of radius 20 millimeters, and Q is equal to 5.3 nanocoulombs, is at location minus 0.02, 0.320 meters. What is the net electric field at 0.3 minus 0.230 meters? All right, so let's highlight the key points. So what we have here is we've got a dipole. These are the Q's and these are the locations. We have a ping pong ball. This is the charge, this is the location. And then we have our observation location. And remember, everything is relative to the observer. Also, you should note we've got a couple units that are going to need converting to SI. Okay, so next up, let's draw a picture. So our observation location A is right here. Our dipole is on axis, and then given to you in the picture, the positive charge is closer. And then we have our ping pong ball with a positive charge here. And so we know, just looking at the electric field, we would know that from the dipole, we would be getting a net field in this direction. And then from the positive charge, we'd have a net field in this direction. So remember, positive radiates out and negative draws the attention to itself. Okay, so to go after this problem, now that we've drawn a picture, we can kind of expect about where our field is going to be. We would then want to do the superposition principle. And that means calculating the fields individually and then summing them up together. So we need E net, which would be equal to E dipole plus E ball. All right, let's start with E dipole. So E dipole, we will want the magnitude of R dipole Because remember, we can just calculate the magnitude of the electric field of the dipole, and then we've already used the picture to determine direction. So let's make our lives easier. So remember, we have observation minus source. So 0.3 minus 0.23, 0 meters, minus 0.02 minus 0.23, 0. And so this is going to be equal to 0.3200, which is 0.32 meters. So in this case, D is much, much larger than the separation, which is basically reasonable for almost every dipole situation unless you're told otherwise. So then we can use the approximation for the electric field on axis of 1 over 4 pi epsilon naught 2 times the electric dipole moment over r cubed, where P is equal to Q times S. Okay, so plugging right along for the electric field from the dipole, we have 9 times 10 to the 9 Newton meters squared. There we go. Per coulomb squared times 2 times 9.8 times 10 to the minus 9 coulombs times 1.2 times 10 to the minus 2 meters. So in this case, we converted nanocoulombs to coulombs, and we converted centimeters into meters, divided by 0.32 meters squared. Cubed. Meters cubed. And so the magnitude of the electric field is equal to, or approximately 64.6 nanocoulombs. We have already determined that it will be going in the positive x direction from our picture. So the electric field of the dipole as a vector is 64.600 newtons per coulomb. Okay, so now we want to go after the electric field of the ball. And remember, we want to go from, R is from the center of the ball. Not the surface. Even though there's no electric field inside of the ball, you still go from the center. And all this will be made clear eventually. Okay, so our ball is equal to 0.3 minus 0.23, 0, minus 0.02, 0.32, 0. And our ball is equal to 0.32 minus 0.550 meters. All right, now we need to go after the magnitude of our ball. So the magnitude of our ball is equal to 0.32 quantity squared plus minus 0.55 quantity squared plus 0 squared. This is equal to 0.63 meters. R hat is equal to R vector over the magnitude. And so this is equal to 0.32 minus 0.550 meters divided by 0.636 meters. And so R hat is equal to 0.503 minus 0.865, 0. And now we can go after the electric field of the ball. We have all the components we need, some of which was given in the problem setup and some of which we just calculated. So this is equal to 1 over 4 pi epsilon naught Q over R magnitude squared times R hat. We can just plug and chug. 9 times 10 to the 9 Newton meters squared over Coulomb squared. 5.3 times 10 to the minus 9 coulombs over 0.636 quantity squared times, I'm going to slide that there, 0.503 minus 0.865, 0 is equal to 120 times, or newtons per coulomb times 0.503 minus 0.8650 is equal to 60.63 minus 1040 newtons per coulomb. And our net electric field is equal to the electric field of the dipole plus the electric field of the ball is equal to 64.600 plus 60.63 minus 1040. There it is, newtons per coulomb. And so E net is equal to 125.23 minus 1040 newtons per coulomb. And now if you wanted to, you could insert any charge into that location and calculate the force on it. All right, so this wraps up section 13.6.